Hello, in this video, we're going to be looking at lesson 7.6, which is on dilations and similarity in the coordinate plane. The essential question that we'll answer is what is a dilation and how are dilations related to similar polygons? Let's start with some important vocabulary for this section. First, what is a dilation? A dilation is a transformation that changes the size of a figure, but not its shape. The original figure that we start with before we apply the transformation is called the pre-image. And the pre-image is always labeled using capital letters, like A, B, C, or in our picture over here, it is P, Q, and R. So the pre-image is what we start with. Then we apply a transformation, and the new figure that is formed after the transformation is called the image. So in our picture right here, the image is triangle P prime, R prime, and Q prime. So we use the same letters, but we use this little like apostrophe symbol, and that's read as prime. So like A prime, B prime, etc. And it's really important to remember that a dilation always makes similar figures. You're changing the size, but not the shape. So all of your angles should look the same, and your sides should just be proportional. I would recommend that you highlight that or put a star by it. It's going to be really important that when we do dilations, we check to make sure that the pre-image and image are similar. Same shape, but different sizes. The scale factor describes how much the figure is enlarged or reduced. We abbreviate the scale factor with the letter K. K is just the letter that's used. Now I'd like you to add to your notes that the scale factor is a multiplier. So it's like, what do I multiply the pre-image by to get to the image? And anytime you multiply by a number that's larger than 1, let's say K is 2. If we dilate a figure by a factor of 2 with a scale factor, it's going to get twice as big. So anytime our K is greater than 1, it's going to get bigger. And anytime the K is below 1, so let's say my scale factor is a half, then it's going to get smaller. Now, the official definition of a scale factor is right here in your notes. It's a ratio of the lengths of the corresponding sides of the image and pre-image. So what's a little different about this from the similarity ratio is you have the second one on top. So like the image length goes on the top of your fraction, and the corresponding length in the pre-image goes in the bottom of your fraction. So it's going to be like the opposite of the similarity ratio. So let's just say in my picture, let's say this is a 2 and this is a 4. Well, my scale factor is 2 because I multiply 2 by 2 and it gets twice as big, it becomes a 4. But the similarity ratio would be the ratio of the original to its image. So the similarity ratio would be 1 over 2, because 2 over 4 reduces to 1/2. So the scale factor is going to be the reciprocal of the similarity ratio. So in this one, my similarity ratio is a half, but my scale factor, K, is 2 over 1. Finally, there's a coordinate rule that we can use for dilations in the coordinate plane, and that is if point xy is the pre-image of a point, so that's what we're starting with, then its image after a dilation with a scale factor of k is the point kx, ky. So all you are doing when you do a dilation is you're multiplying both the x and y coordinates by k. It's a multiplier. And we're going to look at an example here in just a minute. You will be writing a coordinate rule, so this might be a good thing to highlight or underline, put a star by. The coordinate rule for dilations is it maps xy to kx, ky, where we're really just taking the x coordinate times k and the y coordinate times k. So let's go ahead and try a couple examples of some dilations in the coordinate plane. You can see that we are given some points for the polygon, and we want to perform a dilation with the given scale factor. Let's start by just graphing the pre-image. So point A is located at -3, 1. That's the x coordinate and the y coordinate. So I'm going to go -3, then up 1. And then B is at -4, -1. And C is at -2, -1. So when I connect these, I'm going to get a triangle. Make sure that you label the points. I usually label the points at the end just so that I get them to the outside of my shape. So that was A, this one was B, and C. And now that we have our pre-image graphed, we are ready to perform the dilation. Notice that this scale factor is K. K is 2. That's bigger than 1. When we multiply by 2, it's going to get bigger. So I'm going to expect that my image is going to be larger than that blue triangle that I started with. So let's go ahead and write our rule. The rule is just xy maps to, and then kx, ky, well, my k is 2. So I have 2x, 2y. And now let's actually perform the dilation. So for the dilation, we are going to just take each of the coordinates and multiply them by 2. So all the x's, all the y's. So -3 times 2 becomes -6. 1 times 2 becomes 2. And then I'm going to do that with the next point. -4 times 2 is -8. And -1 times 2 is -2. And then here is our last one. And now when we graph the image, we're going to double check to see, does it look like it's the same shape, but just a different size, like twice as big from our scale factor? Let's go ahead and plot our points. -6, 2 is right here. So that's going to be A prime. -8, -2 would be right here, B prime. And -4, -2 is our C prime. And then when I connect that, I get a triangle that looks the same shape as the triangle that we started with, but it's twice as big. Let's try another example. This next one, we have 4 points, so it's going to make a quadrilateral. Let's plot the pre-image first. I'm going to put the points in green. So -10, 0, -5, 0, 0, 5, and -5, 5. All right, now that I've made my shape, I'm going to label the corners here. So I have P was that one, Q, -5, 0. Here's R and S. And now we're going to do the dilation. This time, notice that K is 1/5. Well, 1/5 is below 1, so it's going to get smaller. So we need to, for our rule, take the point xy and multiply both the x and y coordinates by 1/5. So 1/5 x, 1/5 y. Let's do it. So when I multiply by 1/5, I know that might sound kind of scary with the fractions, but remember, -5 times 1/5, you really just need to multiply numerators and denominators. And when I multiply by 1, it stays the same, -10, and then 1 times 5 is 5. So really, all it is -10 divided by 5, which is -2. Multiplying by 1/5 is the same as dividing by 5. Just like multiplying by 1/2 is the same as dividing by 2. Now notice the 0. 0 is the one thing that doesn't change when you apply a scale factor, because 0 times any number is always 0. So all of our zeros are going to stay the same, but all of the other numbers are going to change. So -5, again, I'm going to divide that by 5. We get -1. 5 divided by 5 is 1, -1, and 1. And if you need to, you can always use a calculator to help with that. You could even convert 1/5 to a decimal. If you do 1 divided by 5, it's 0.2. All right, I'm ready to plot my image now. So negative 10, or negative 2, 0 is right there. Negative 1, 0, 0, 1, and negative 1, 1. So notice that it got a whole lot smaller. It's 1/5 of the size that we started with, but it does still appear to be the same shape, just a much smaller size. And then don't forget to label your image with the same letters as the pre-image, but you use that little prime symbol. So P prime, Q prime, R prime, and S prime. Here's a try now. You are going to just perform a dilation of a scale factor of 1/2. You don't have to make the graph. You just need to find the new points. So D at 4, negative 2. I just want you to figure out what are the coordinates of D prime if you apply the scale factor of 1/2. So I'm going to have you pause the video now and then try this on your own. And then when you hit play again, the answers will be posted. Please pause now. Okay, here are your solutions. You can take the x and y coordinates times 1/2, or if you want to put it in your calculator, if you need help with that, it might be helpful or a little quicker, I guess, if you just change a half to 0.5. But you never want to round when you're switching a fraction to a decimal. So for example, if I was multiplying by 1/3, I wouldn't want to change it to 0.3 because that's rounded. 1/3 is 0.3 repeating, so it'd be much better to just divide by 2. So when I did this, I really just took all my points, multiplied by a half, I divided them by 2, and that's how I got those values. The last example that we're going to look at in this section has to do with some dilations in the coordinate plane again, but this time we're going to find a missing coordinate in some similar triangles. Notice the similarity statement right here says triangle TUO is similar to triangle RSO. I'm going to outline these triangles in different colors so we can see them because they do overlap. TOU or TUO is this smaller triangle. And then RSO, I'll outline in blue, is this triangle right here. Now you might be thinking, I don't know any dimensions, so how can I find a missing value? But if we look at the corner here being like the origin, this is the point 0, 0. If we want to know how far is it to -9, like for this little triangle, 0 to -9 is just the absolute value of the difference between the coordinates. So it's not -9, but +9. So distances are always positive. And the point R in the bigger triangle is going to be at -12, 0. So that's 12 away from the origin. And then we can do the same thing on the other side, but I'm missing U. So we'll have to figure out what U is. But we do know that this value here is 16. So kind of think of it like we have our small and we have our big. And there's a lot of different ways that you can do this problem. Let's start with the similarity ratio, which is what we're familiar with from the rest of this chapter. So for the similarity ratio, you're going to do A over B, where A is in the first triangle and B is in the second triangle. So A is going to be the small number, B is going to be the bigger number. Now let's go ahead and look at some parts where we have matches. So TO, this 9 right here, corresponds with RO in the bigger triangle, which is 12. So for my A over B ratio, I'm looking at TO over RO. Those are the corresponding parts, and that's 9 over 12, which we can reduce either with the fraction button or just by dividing by 3. And that gives us a similarity ratio of 3 over 4. So that right there is our similarity ratio. Now to find the scale factor, it's pretty quick to find the scale factor because the scale factor is just the multiplier. So how do you get from here to here? Let me just kind of move this down. So it's like, what do I multiply the TUO number by to get to the RSO? Well, if I multiply 9 by 3 over 4, 9 is going to get smaller. But if I do the reciprocal of 3 over 4 and I multiply by 4 over 3, that's going to give us the next value. So the scale factor is always just the reciprocal of the similarity ratio. And remember, we abbreviate scale factor with a K, so I'm going to go K equals 4/3. And now that we have those figured out, let's go ahead and find our coordinates of U. And there's definitely a lot of different ways that you could do this. You could use the similarity ratios. You could use the proportions. I guess I'm just going to go back to the similarity ratio of 3/4 so that we can use a proportion, which you've gotten really good at this chapter. So the 3, remember, was the small triangle, and the 4 was the big triangle. So if I look over here in my picture, this 16, which is SO, 16, is part of the big triangle. So I have to put the 16 right here. And then UO is what we're trying to figure out. So this is like my missing piece right here. UO is X. And I'm just going to use the letter U here. And now let's go ahead and solve this. And there's a lot of different ways we could solve this. You can find a pattern. You can use your cross products. I'm going to go ahead and just do the cross product here quick. So 3 times 16 equals 4 times U. That's 48 equals 4U. We divide by 4, and we get 12. For my final answer, I'm almost done. I just need to make sure that I write the coordinates of U. So we have to go back to an ordered pair. Notice that U is along the y-axis, so it's going to be 0, and then the value we just calculated was 12. Let's look at one more example here for the try now. So similar problem, triangle AEB is similar to triangle CED. You're going to find the similarity ratio, the scale factor, and the coordinates of C. Now there is more than one way to do it, so definitely don't feel like you have to do a proportion. I know that this one, the pattern, I think is a little bit more clear of what's going on. When you go from the small triangle AEB to the big triangle CED, that's the outermost. So please pause your video now, and then when you hit play again, I will have the answers posted. Please pause your video. Okay, here is your solution. The similarity ratio is 1/3. The 3/9 makes 1/3. You can also probably pretty clearly see that the multiplier is going to be 3 because 3 times 3 is 9. So the scale factor, remember, is just the reciprocal of the similarity ratio. So 1/3 becomes 3/1 or just 3. And then I definitely could just take this 2 and times by 3, and that would give me the 6 as well. If you want to use the proportion like we've been practicing this chapter, you've gotten good at those. I have the work shown right here for that. You also end up with 6. So C is at 0.6. This is it for lesson 7.6, and you just completed the last lesson of our similarity unit. Good luck as you practice some dilations on your own. Thanks for watching. Bye.